Welcome back to Calculus 1. This is the second part of our lecture on optimization. Continuing where we left off in part 1, we're going to get right into some more complicated optimization problems. All right, now before we get to those following two more complicated questions that we'll look at, let's go through maybe some unfamiliar formulas that typically pop up in optimization problems, at least the ones that are more complicated. The first two examples we looked at dealt with finding maximum area for a rectangle and then maximum volume for a rectangular box. And the area formula and volume formulas are both rather simple, and most students know those. Some of the examples we'll be getting to require you to minimize distance or minimize the distance traveled, and our starting place for that is usually something called the distance formula. You probably last saw this in an algebra course, so let's kind of review that before we get to the more complicated examples. All right, so we're interested here in finding the distance between two ordered pairs, x1 comma y1 and x2 comma y2. Same notation for ordered pairs. We're not calculating slope. We're interested in finding that distance d between those 2 points sketched there in quadrant 1. They could be anywhere. This is just a sample sketch. Now, hopefully you know the formula, but if not, you basically create a right triangle and then apply the Pythagorean theorem. The side lengths of your right triangle here, the kind of base length, is the difference in the x-coordinates, x2 minus x1. The height is the difference in the y-coordinates, y2 minus y1. And then you apply the Pythagorean theorem, and you can easily solve for the distance, the hypotenuse, by taking a square root. We're going to look at an example where this is going to be kind of our starting place for the formula. But there are some other examples that want you to minimize maybe the time involved or minimize total travel time. So let's review what might be referred to as the rate equation relating distance, your speed or rate of travel, and then the time for which that occurs. All right, so let's denote by the distance traveled, d, our speed or rate, r, and then time as t. Now, in order for this formula to be valid, if you went through some physics courses, your speed or rate has to be constant, which we're going to assume for our calculus problems. And we get this basic equation, d equals rt, or distance equals rate times time. Now, we might need a manipulated version for this, kind of in the near future. I have no idea where you might encounter that. So we might be interested in solving this for time. We can do that, no problem. Just divide, and you get a kind of an alternate version. Time equals distance traveled divided by your rate or speed. All right, with that out of the way, let's go ahead and get into our first, more complicated example. We'll label this example 3, continuing from last time. You probably want to go back and review the steps that we set out for optimization problems, about drawing a sketch, assigning variables, determining what quantity is going to be optimized, what quantity is being maximized or minimized, and then finding a formula. Definitely review those and have those handy through the next two examples. Okay, this one is kind of medium difficulty. It's a simple problem to state. Find the point on the graph of y equals square root of x that is closest to the point on the positive x-axis, 3, 0. Now, give yourself several minutes to attempt this. Pause the video and we'll check back in. The first thing we'll give is a hint for the sketch in case we're stuck. We'll check in a few minutes. All right, let's go through the sketch. Maybe that'll be enough to get you through kind of setting up the rest of the problem. The sketch is rather simple. We have our basic square root graph, kind of a parabola turned on its side. We have a fixed point on the positive x-axis, 3 comma 0, and then a variable unknown point that can be anywhere along that curve, the square root function. Now I drew kind of in black there what seems to be, just by eyeballing, kind of where the closest point on that square root function's graph should be to 3 comma 0. And you can see if you go a little bit further to the right in red, you get a larger distance, and same if you go a little further to the left. So we kind of can eyeball it and see that we should expect something. It looks like from this quick sketch, we should expect an x-coordinate somewhere between 2 and 3. Now we actually can make the distance as big as we want. If you let that point go all the way to the right, the distance can increase towards infinity and become almost infinitely long if you let that go far enough to the right. All right, now at this point with the sketch and the clue here being we're asked to find the point that is closest, that's asking us in a kind of a different way to minimize the distance between those points. So see if with this sketch and your distance formula, if you can kind of go through the rest of the problem that we addressed with the steps for optimization. We'll check in a few minutes. Welcome back. Hopefully you were successful. At this point with our distance formula that we reviewed a few minutes ago, it's kind of plug and chug. We have 2 ordered pairs with the coordinates 3 comma 0 and x comma y. Granted, we don't know what x and y are yet, but we can plug those in to our distance formula. And we get this expression, the square root of x minus 3 squared plus y squared. Now, like what we saw in example 1 and example 2, there's an immediate problem with our formula or equation here. It contains 2 variables. We are only dealing with single variable calculus right now. We can't optimize a function of 2 or more variables yet. That requires multivariable calculus, Calc 3. So we have to go through our usual trick of trying to eliminate one of these variables with a constraint. Now, how do we do that? Well, notice we haven't used some information from the problem. The unknown point that we're looking for has to be on the graph of y equals square root of x. In other words, our point that we're looking for is constrained to lie along that curve. So the y equals square root of x is basically our constraint, since we're requiring this point to be on the graph of that function. So here we can just plug that in. Notice the distance formula contains y squared, square of square root. They cancel out, leaving you with basically just x there. So we get as our distance formula this expression, which is a square root. Now I want to give you kind of a little shortcut, a nice little tip that you could apply here, but you don't have to. You could proceed from here. We now have a function defined in terms of only one variable, and we could find the derivative of this, but it's kind of a square root expression, and that's going to lead to something that looks a little complicated perhaps. So let's get to a shortcut, and let's first start this shortcut by asking a simple, unrelated question: which is smaller, square root of 5 or square root of 7? Now you don't need a calculator for this. Square root values get bigger as the inside gets bigger. Inversely, a square root gets smaller as the inside gets smaller. So which of these is the smaller number? Square root of 5, since the inside 5 is less than the other inside 7. Now, how does this help us for our problem? If we're trying to minimize this square root function, it's equivalent for us to minimize the quantity inside the square root. Now, we don't have to do this, but it gives us a simpler function to differentiate. If we take a look at the inner expression as a function of x, we can write this without a square root. The inside is just x minus 3 squared plus x. And that's going to be a lot easier to differentiate with the rest of the steps for optimization, finding the derivative, finding the critical points, and finishing it from there. So let's use the inner expression instead of the expression for d of x, which is the actual distance involving the square root. You can do that. You'll end up with the same results. It's just a little bit more work. Now, maybe pause the video to make one last attempt if you got stuck anywhere before. It should be very simple using this expression f of x, the inside of the square root, to minimize that by finding the derivative and then the critical points. We'll check in about a minute. All right, let's go ahead and finish this. The derivative should be pretty straightforward. You could multiply the expression for f of x out, FOIL or expand that, but we're going to use the chain rule. So bring the 2 down, then subtract 1 from the exponent. Don't forget about the derivative of x, which would become 1. So we get as our derivative 2 times the quantity x minus 3 plus 1. That's never undefined, so we can jump straight to finding where that derivative equals 0 to get critical points. The steps here should be pretty straightforward. Set that derivative equal to 0, subtract 1, divide by 2, and then add 3. And you should find your x-coordinate as 5/2, which is 2.5, which is what we expected an x-coordinate just by eyeballing in our sketch, somewhere between 2 and 3. Now, by itself, the x-coordinate is not a complete answer. The question wants us to find the point in order to pair an x comma y. So take your x-coordinate, plug it back into the function or equation. Our point has to be on the graph of y equals square root of x. So our y value would be square root of 5/2. And we get our coordinates for our point, 5/2 comma square root of 5/2. All right, now this one was medium difficulty. It was probably very difficult if you didn't know the distance formula. With the distance formula, the work is rather minimal. Let's get to a final, more complicated example. Example 4 that we'll be getting to is probably one of the more complicated optimization problems that I could expect a student in their first calculus course to answer. We'll go through it. You'll want to give yourself a lot of time for it. Let's go ahead to example 4. Notice immediately the statement of the problem seems a lot longer. That doesn't always imply that the problem is more complicated, but here it does. There's some algebraic complications, which we'll see as we go through this, but pause the video, make an attempt. We'll check in a few minutes. The first thing I'll give as a hint, if you were stuck, is the sketch. All right, hopefully you have the sketch. What the problem is basically asking is you're trying to go from a point on the shoreline through a combination of running and swimming to an island 2 miles offshore. Now you can run at 8 miles per hour. You can swim at 3 miles per hour. So you want to kind of optimize how far you're running with your rate for swimming, which is a little bit less. So you probably want to run more than you swim, since you can run faster than you can swim. All right, there's some extra complications here just to get the sketch right, which we'll put up. So the setup is we kind of have a straight shoreline. There's a cabin that we're staying at. And then 6 miles down the shore, there's a point which, if we go directly 2 miles off the shore, we reach an island. All right, we're going to call the unknown distance that we're running x. So we're going to run x miles down the shore. And then at a certain point, after we've ran x miles, we're going to transition to swimming the remaining distance, which we're denoting y. All right, now if we denote the distance we run by x, notice the part left over to that point would be 6 minus x. In order to find the time it takes to reach the island in as short a time as possible, we want to minimize the two different parts. We want to minimize the time it takes for us to run combined with the time it takes for us to swim. So maybe with the sketch, and now that hint that you want to split this up to two parts, you can maybe start to find some equations or formulas. Maybe think back to some things we reviewed earlier. Oh, I don't know, maybe something from the first part about the rate equation. We'll check in a few minutes. All right, let's go through finding equations or formulas. The key here is that we're trying to minimize time. So our equations that we're coming up with should say something about a combination of time, distance traveled, and the given rates that we have. And as it turns out, the rate equation works perfectly. We're going to use that here in the manipulated version. Time traveled equals the distance traveled divided by our rate. We're going to apply that twice, once to the part where we're running, and then again to the part when we're swimming. If we apply that, we have our rate for running, which is 8 miles per hour. We run an unknown x miles, so we get this time here, x divided by 8. We apply that again for the part where we're swimming. We swim at 3 miles per hour for our rate, and then we swim a distance, still unknown, of y miles. We add those two results together. That is basically our formula, function, or equation, but again, it contains two variables. Now, you might want to pause the video to see if you can come up with the constraint. Take a look at the second part kind of the sketch with the island and the distance y, and see if you can find a secondary equation that relates x, y, and that given 2 miles. We'll check in about a minute. All right, let's take a look at that swimming part of our journey. We get a nice right triangle. It's been a while since we mentioned some equations or formulas when we first addressed related rates earlier in the course. But we mentioned back then, if we draw a sketch and we see a right triangle, chances are we can probably apply the Pythagorean theorem. And as it turns out, we can. We have the base length as 6 minus x, the hypotenuse as y, and then the height as that fixed 2 miles from the island being 2 miles offshore. Okay, if you apply the Pythagorean theorem, you get an expression for y in terms of x. We can plug that in to the time formula above, the time for running plus the time plus swimming, and we get now an expression for time that is only a function of x. Now, before we go through the rest of it, I want to mention two things. The previous example, example 3, we mentioned a trick about minimizing the inside. We can't do that here since our function is not an entire square root. We only have part of our function or formula as a square root expression. So we can't apply that trick about minimizing the inside here. The other thing I want to mention is we have an interval of relevant x values to find the kind of length that we have to run down the shore that minimizes the total time. We wouldn't want to run more than 6 miles. That would require us to run past basically the point on the shore. That's 2 miles off the coast. And then we'd have to swim backwards. Now, you'll reach the island eventually, but it's not going to be in as short a time as possible. So hopefully you can see here the distance we run down the shore should be somewhere between 0 and 6 miles. So we have an interval here that'll come back once we get through some algebra involved in finding the critical points. Now, since we have now a properly defined optimization problem, we have a function, we have an interval, you can probably complete it from here, find the derivative, and then find the critical points. Finding the critical points gets to be algebraically intense. So give yourself maybe a few more minutes to complete this. We'll go through it and then wrap this lecture up. We'll check in a few minutes. All right, let's go ahead and finish the problem. So pretty much from here, we want to find the derivative for this expression, the time, as a function of x. All right, we can rewrite that square root as a 1/2 power, and then we can apply the chain rule. This gets a little tricky because it's several functions inside functions. It's a multiply composite function, functions inside functions, inside functions. If you apply the chain rule, bring that 1/2 power down, subtract 1 from that to get an external -1/2 power. The inside remains the same. And then you multiply by the derivative of the inside being what's inside the brackets there. And that requires the chain rule yet again. The inside part has the part in parentheses. We bring the exponent 2 down, keep the inside the same, 6 minus x. The power drops from 2 to 1, but notice the derivative of the inside, 6 minus x, gives us an extra factor, another derivative of the inside of -1. Now, hopefully you're comfortable with that after all the time we spent on looking at differentiation rules. The first term in t as a function of x, 1/8 x, that just differentiates to 1/8. So we have our derivative here. Before we get to finding the critical points, we're going to want to simplify that. We can clean this up a little bit. Notice the factor of 2 and the factor of 1/2 cancel, since we're multiplying all the way through. And the external -1/2 power, we can use that to rewrite that as a square root in a denominator. That's going to make some of the algebraic steps we'll get through as simple and as obvious to perform as possible. Now, if you simplify, you get this version for the derivative. From here, we're going to find the critical points by seeing where this derivative equals 0. As it turns out, since that denominator inside the square root is 6 minus x squared, we don't have to worry about that ever taking on 0 as the part inside that denominator. So there's never a chance for this expression to become undefined. So we jump straight to setting this derivative equal to 0. And this is where some fundamentals from algebra hopefully kick in. Now, this is where the problem is yet again difficult, since there's kind of a lot of work kind of from here on out. The first thing we want to do probably is get rid of fractions. We can add the square root fraction to the left side. And then we can basically cross multiply. All right, since we end up with a square root expression, a radical, we can undo that by squaring both sides. Be careful, you have kind of some factors there, you're multiplying. You would want to square each factor. Be careful and square the factor of 3 on the right-hand side, as well as squaring both factors on the left side. All right, so we should end up with here. We could multiply this all out and try to solve for x. You might be able to see here you have some sort of quadratic equation. What's going to be a little bit simpler, notice on both sides you have the quantity 6 minus x squared. Now, try to solve for that. Don't worry about trying to solve for x. That's going to take some good amount of time to expand or FOIL those expressions. Try to first solve for the quantity 6 minus x squared. We'll check in a few seconds. All right, hopefully that went pretty quick. You can try to directly solve for x. We're going to minimize some of the algebraic steps by first solving for 6 minus x squared. Distribute that 9 through the brackets, and then you can notice you have the quantity on both sides. To solve for that, get the quantity all on one side, we can subtract 9 times 6 minus x squared to the left side. You can subtract those like terms by subtracting their coefficients. 64 minus 9 gives you the coefficient of 55 there. From here, this looks like something what you might have last encountered when dealing with completing the square. We can solve for the squared expression by dividing by 55. We get 6 minus x squared equals 36 divided by 55. And at this point, we can undo the square by taking a square root. Don't forget, when you take a square root, you need to account for going backwards with the plus or minus. There's going to be 2 solutions, the positive and negative square root. And if you finish that with a few algebraic details left to you for solving for x, you should find that you get the 2 x values, 6 plus or minus the square root of 36 divided by 55. And if you apply your properties of square roots, you can express that square root as 6. That's the square root of 36 in the numerator, divided by square root of 55. And I will tell you, it is completely fine to have a square root in a denominator. If anybody told you otherwise, you were lied to. So it's totally fine to have square root of 55 in the denominator. Now, this gives you 2 solutions. We need to think back to our problem when we set this up. We mentioned we only really need to consider x values, the distance that we run down the shore, that are between 0 and 6. You can have x values for this problem greater than 6 miles. That's not going to minimize the total time. Now, the 2 versions here pertain to the solution with the plus between and the solution with the minus. I don't even care what the value of 6 divided by square root of 55 is. That is some positive number. Add that positive number to 6, you then get a number bigger than 6. So that first solution, the version with the plus between, is actually outside of our interval 0 to 6. So you can kind of rule that out. That's going to be an acceptable value that gets you to the island, but it doesn't minimize the time. The solution with the minus, however, stays within the interval 0 to 6. And as it turns out, that does minimize the total time. If we approximate that, we get that we have to run about 5.19 miles down the shore, and then we swim the remaining distance diagonally off towards the island.